Assalamualaikum and good morning. I wish to all the panels. My name is Muhammad Haziq bin Mazalan, and today I'm going to present on the design of a radio-controlled polystyrene aeroplane model and evaporative pattern casting mold, supervised by Dr. Zulkifli bin Haji Muhammad. Problem arise when there is an increase in demand of radio-controlled aeroplane model as a hobby, but yet to be explored by nations. Plus, there is low to almost none small-scale radio-controlled aeroplane model productions as comparison to manufacturers produced by big companies. Third, there is lacks of information in the production of small-scale RC aeroplane model using expanded polystyrene or EPS mold. Hence, the objective of this project is to design and analyze radio-controlled polystyrene aeroplane model and evaporative pattern casting (EPC) aeroplane mold. The scope of study is number 1, design polystyrene RC aeroplane model and EPC aeroplane mold. Number 2, study the mechanical, fluid, thermodynamic flow of the aeroplane and the mold. Number 3, evaluate the overall design of the aeroplane and the mold with suggestions of future improvements. Before we move on to the design, first we need to understand how does the fabrication of EPS works. Pre-expanded polystyrene beads is put into the mold and then closed and subjected to high steam temperature and high pressure. With the high steam, the EPS beads is then combined together, or I would say fused together, to produce an EPS production. After that, a cooling process of the mold happens as a curing process to the mold and the EPS products. Hence, the EPS is produced. Okay, here we can see that the spherical shape as compared to polyhedral shape. What is the difference? Well, having in figure A will produce more brittle structure, and in figure B, the polyhedral shape means that we produce more fused EPS beads, means that they fuse together well, increase the mechanical properties of the EPS. So what are the factors affecting this? There are 5 major factors, and this is affected by steam temperature, steam pressure, steam flow rate, time of exposure to the steam, and the density of the polystyrene. All these factors need to be remembered because we will use it in the simulation later on. And like I said, the temperature of the steam, the ideal temperature of the steam is between 100 to 120 degrees Celsius. And here, 0.6 bars to 2.5 bars, having relatively slow flow rate to increase the diffusion rate or fusion rate of the beads. Time of exposure between 30 seconds up to 1 minute, and then the density of polystyrene is high. After chapter 1 and chapter 2, come to chapter 3, where we start to design. Before we design the aeroplane mold, first we need to design the aeroplane model. This is because the aeroplane mold is based on the aeroplane design. We have 3 designs here. As you can see here, I put here a 3 little design, a trainer, glider, and delta. All this design is based on the PDS, or I should say product design specification, and then is evaluated. So a process is applied to the aeroplane mold, and then we come to the next part where we start to analyze all this design. We will analyze based on its thermodynamic, mechanical properties, and fluid dynamics of the aeroplane and the mold design. Start with the discussion and then some safety precautions and recommendations. We go on to the result and discussion. So here is the final design of the aeroplane model. You can see here I'm using delta wing aeroplane and having a swept back wing with a symmetrical aerofoil shaped wing. The elevation and the electronic platform is made of balsa wood, which is low density, and then we have the motor made of outrunner, which have high RPM relative to the weight, and then wing frame within the aeroplane, and we use a transmitter of DSRX11. So here is the aeroplane exploded view. We can see here that let me highlight this. Okay, here is the aeroplane front part, which is contain the electronic parts to control the elevation here using the rod here, and then this is the motor. So all these components combine together to produce RC aeroplane. Now this is the finalized design of the mold. You can see it has an aerofoil shaped mold. We need to use manual feeding, and it is holded together by bolt and nut as a fastening mechanism. The aerofoil shape will ease the steam flow through the mold, having a total of 2,550 holes in the mold surfaces to increase the steam flow in the mold cavities, and of course corrosion resistant due to the high steam temperature. So here we can see that the mold cope and drag of the mold, aeroplane mold, we can see here this is a mold cavity, and we have some bolts and nuts and washers. So the mold material selection. Mold properties must have low density, able to withstand high pressure, have high specific heat capacity, high corrosion resistance, and have high machinability rate. Based on my research and findings on the literature review, all the manufacturers use aluminium 6063. Yes. This is because it has very good machinability rate, high resistance, and most importantly, high specific heat capacity, because it needs to heat up slowly and then cool down slowly to cook up the bits. Next, we start on the simulation. The design of the aeroplane is not just simply by logic. We need to calculate all the dimensions. As you can see here, the root chord, thick chord, sweep, and wingspan is all calculated. The density is then calculated and produce a total of mass divided by volume having density. Aeroplane mass is 18.48. That is relatively very low. So as you can see on the right, that is a square shape. Let me highlight this. This is square shape, causing a center of gravity in the middle, and then having this means that the wing will rotate in the center of gravity, or the center of gravity exists. When we put the center of gravity here, means that it will move forward, which is good. As you can see, having all the assemblies assembled together with the electronic parts and everything, the center of gravity is still in the middle, so this is good. Next, we move on to the aerodynamics. Dear panels, Bernoulli principle stated that having a higher pressure means having low velocity, or the other way around. Higher pressure, or faster velocity will cause low pressure. As you can see in the top view of the aeroplane wing, you can see relatively very high velocity here. You see red, and then let me use red pointer so we can see it better. Okay, here, and then as compared to here, this is low velocity, but you can see the total pressure is different, because here is the high pressure, and the bottom pressure, it has more, meaning that it has larger lifting force, and the aerodynamic is good. So here you can see in detail that at the bottom of the wing there is a layer of lifting force to the aeroplane model, and I'm using HS522 as the chord and the MH60 as the tip. Okay, this is the overall simulation of the aeroplane model. Okay, now we move on to the aeroplane mold pressure analysis. The aerofoil shape is so the dimension, the mold will be subjected to a pressure up to 200 kilopascal. And then, so in discussing this, because aluminium has relatively low yield strength, which is 160, I set safety factor of 2 and making allowable yield stress 80 megapascal. This will subjected to 120 degrees Celsius temperature and 200 kilopascal pressure. And we can see from the result, we can see that all the maximum stress, the maximum displacement, and the maximum strain occur at the first chord. So you can see here, the main reason is because it has more curvy shape as compared to the tip chord. This causes the total stress, this total structure stress is combined by stress bending and also internal stress. Having a aerofoil shape causes it to experience more bending stress. Okay, here the comparison between the cope and the drag. Obviously, the cope is the top, causing it has a higher amount of stress because it has more curvy shape as compared to the bottom. Similar trend line can be seen in the max displacement, ranging between 200 to 300 kilopascal. Now we go to the steam flow analysis. On the steam flow, we subjected a total of 0.1 steam velocity at temperature of 120 degrees Celsius, 200 kilopascal. You can see a steam flow from the bottom of the mold because the steam will flow up and then go into the mold and then expand the beads. So here you can see it flow very smooth, and then here from the top view of the mold you can see the steam is flowing out from the holes. This is very good because you can see that the flow is evenly spreaded inside the mold cavity. See, so the steam velocity analysis, you can see there is a high peak and then two high peak, which is the steam flowing into the mold holes, and then an average of 0.3. You can see the steam flowing in from the bottom and then steam flowing out from the top view. Okay, as mentioned before, the wall heats up, the material, the mold wall heats up to 170 degrees Celsius average. However, you can see here in the beginning that it doesn't reach that temperature first. This is because it has a high specific heat capacity, which is good because we don't want to overburn the EPS beads, causing it to shrinkage. There are all the panels. Based on the SolidWorks simulations, the overall design of the RC aeroplane model and the mold is accepted. The aeroplane design is proven to be lightweight, high aerodynamic, and can withstand multiple loadings. The mold design also shown a smooth flow of the steam throughout the mold's cavity and can withstand high pressure. As my recommendation, I suggest to put Teflon coating in the internal cavity region of the mold to avoid polystyrene sticking onto the mold surface, air-gun polystyrene feeding system to decrease the preparation time of the molding process, and larger steam chest for bigger and better aeroplane design. That's all from me. Thank you for lending your ears. Thank you and stay safe.